Hi guys, and welcome back to Elevate Chem. It's Jesse here with another concept video. Now this is the first video of a 5-part series which will be covering stoichiometry and is really designed to sort of summarize all of the information we've gotten so far and put it all together. Now as always, we're going to be looking at exam questions because ultimately the best way to apply your knowledge is in an actual exam. Now the first thing I want you to do is to have a go at this question. It's from the WACE 2012 chemistry exam, stage 3, and it's question 41. So pause the video now and have a go. Fantastic. I hope you guys went well, but there's certainly some bits in this question that made our lives a lot more difficult than it might have been otherwise. The big thing that I noticed right off the back is there is a monstrous amount of text written here. And it can certainly seem quite daunting walking into an exam and feeling like you need to understand and memorize every single thing that's written here. Guys, I'm going to tell you right up, we don't need to understand everything that is written here, and 9 times out of 10, there's a lot of filler text within the question. Personally, what I'm going to do to tackle this question is, for right now, ignore all of that text. And the reason why is I want to see what the question is actually first, so I can identify the key bits within that question. So, the first question asks, how many moles of NH4NO3 are produced by the reaction of 1 mole of CH4? Now I'm going to identify the key words within there, or in this case, I guess, the key molecules. And that is NH4NO3 and CH4. And I'm going to look through the question text and try and identify those molecules. And I can see that one of them was a product and one of them was a reactant. Awesome. Now if I read the rest of the question, it talks about the fact that all of these steps are part of a process, and that means these steps are feeding into one another, and the overall, you could almost write an overall reaction for this process. So as we see, CH4 plus water, but I'm not really concerned about that right now, gives us hydrogen gas and carbon monoxide gas. And if you look into step 2, you can see that actually only the hydrogen gas is used. This carbon monoxide is no longer used, and that's a trend that continues throughout all of these steps. So my hydrogen gas, again, there's nitrogen gas as well, but I'm not really concerned about that because my methane, my CH4, doesn't produce it. That gives me NH3. My NH3 is then used here, plus some additional oxygen. Again, not concerned about it. And then following this down, identifying the key reactants and products respectively, I find that those are the molecular species I'm going to need to be concerned with. So how am I going to work out how many moles are produced by each mole of CH4? Well, we know that this concept at least stems from stoichiometry and the molar ratios. But what am I going to do when I have so many steps? Well, all we're going to do is identify the molar ratios from each of the steps and then see if we can cancel out or simplify or summarize all of those ratios. So initially, from CH4 to H2, we have a 1:3 ratio. And then in step 2, we have 3H2 going to 2NH3. And again, I'm only concerned with the molar ratios for those key reactants and products that I've underlined, which continue throughout the rest of the process. For step 3, I have 4:4. Step 4, 2:2. Step 5, another 4:4. And finally, step 6, a 1:1. So the first thing to identify here, guys, is that any time you have two numbers which are equal to one another, it's the same as a 1:1 reaction. So that means this 4:4 is actually equivalent to a 1:1. And the same can be said for this 2:2. We've got another example of a 4:4 here, so that's also a 1:1. And my 1:1 is, again, a 1:1. So all of these reactions here ultimately are a 1:1. And how you simplify these molar ratios is by actually multiplying them together. So what I'm going to do is multiply my 1 times my 1 times my 1 times my 1. So that means that these 4 steps together have an overall molar ratio of 1:1. And what that means is for each mole of my NH3 right up the top here. For each mole of my NH3, I will get 1 mole of NH4NO3. That's what this overall 1-to-1 ratio means. Now let's apply a similar sort of process or a similar sort of logic to steps 1 to 2. We can see that initially we have 1 to 3, and then we have 3 to 2. And again, what we can do here is multiply through these molar ratios, and what that essentially does is cancels them out. So another way of writing these ratios is as a third, and then this following ratio in step 2 would be written as 3 on 2. And multiplying them together, the 3's cancel out, and overall we're given a ratio of 1 on 2, and another way of writing that is a 1 to 2 ratio. So in total, if we now wish to multiply these two together, what we're going to yield with overall is a 1 to 2 ratio. And the reason why is because this 1-to-1 ratio has no effect on the moles produced. But this initial one, 1 to 2, does. It doubles the amount of moles produced. So that means for every 1 mole of CH4 gas, we'll get overall 2 moles of NH3. And for these 2 moles of NH3, we'll get 2 moles of NH4NO3. So, following through, we start off with 1 mole of CH4. We can see it's an overall 1 to 2 molar ratio. So that means we will have overall 2 moles of NH4NO3 produced. Awesome. On to the next part of the question. Calculate the mass of CH4 required to produce 2.5 by 10 to the 5 tons of NH4NO3. Assume all reactions are 100% efficient, good, and express your answer to 3 significant figures. So firstly, the fact that it says assume all reactions are 100% efficient, what that really means is if we go back to these steps, we can see that all of these reactions are equilibrium reactions because they have these double-headed arrows. Now, by saying they're 100% efficient, we actually assume they're not equilibrium reactions anymore, and we actually assume they completely go to the right, which is very useful for us, or otherwise we really wouldn't be able to tackle this question. So, when I read this question, I see that I'm given a mass here, and I don't really know ultimately what I'm going to be doing yet, but I know I've got a mass, and I should pretty much always work with moles. So the first thing right off I'm going to do is convert this mass into moles. So, how do I convert mass into moles? Of course, I'm going to need a molar mass. Unfortunately, it's not provided to us. So we're going to have to work it out. So the molar mass of NH4NO3 is equal to, and again, unfortunately, it's not provided. So what we're going to have to do is look in our periodic table of elements. And for that, I'm going to find that it is 2 times 14.01 plus 3 times 16 plus 4 times 1.008. Now your periodic table might be more or less accurate than the one I'm using, so keep that in mind. But for me, these are the values that I obtained for the molar mass for each of those elements, and of course I'm multiplying them by the number of times they occur within this molecule. Doing this quick equation, guys, I get 80.052 grams per mole as my molar mass for this species. Now the moles is equal to my mass divided by molar mass. So that is equal to 2.50 by 10 to the 5. Now that's in tons. And we can see that my molar mass is actually grams per mole, which means I'm going to need to convert my tons into grams. And how I do that is by simply multiplying by 10 to the 6. So now that's my mass in grams, and dividing by my molar mass, 80.052, gives me a value of 3.12297, and then there's many digits later after that, by 10 to the 9 moles of NH4NO3. Now why I stopped writing after 5 decimal points there, guys, is because it says there in the question, express your answer to 3 significant figures. And that means that I'm really not going to need more digits than that. However, it's important to keep in your calculator, not necessarily write down because you won't be marked on that, but keep in your calculator as many digits as possible to make sure you actually have that accuracy. Awesome. So let's continue with the question. We're looking for the mass of CH4, and that means I'm going to need the moles of CH4 first. And how do I work out the moles of CH4 from the moles of NH4NO3? Well, thankfully, we actually worked out the molar ratio in the previous question, and often questions are designed like this. If you look at the question, you're like, man, I have to work out the molar ratio between CH4 and NH4NO3. That's going to take me ages. You probably just worked it out in a prior part of the question. So we know it's a 1:2 ratio, so that means we're going to have to divide this number by 2. So moles of CH4 equals half moles of NH4NO3 equals 0.5 times that previous number that we've got just up here. So that means it will equal 1.561485, and there's more digits, by 10 to the 9 moles. And that's how many moles of methane there are. Now again, I'm trying to get the mass. So how I get the mass from the moles? The molar mass of CH4 is equal to 12.01 plus 4 times 1.008. Same method as before. And that equals 16.042 grams per mole. And I'm going to write it this way. Both ways are more than acceptable. So therefore, the mass of CH4 is equal to my moles times my molar mass. Plugging in both of those numbers and multiplying through, 1.56, I've just abbreviated here to make my life easier, by 10 to the 9 times 16.042 gives us a final mass of 2.504934 and more digits by 10 to the 10 grams. Now I'm going to leave my answer in grams, and the reason why is because that is the standard unit for chemistry. However, it says express your answer to 3 significant figures. So that means my final answer is going to be mass CH4 equals 2.50 by 10 to the 10 grams. 3 significant figures being these 3 first digits here. And I usually write, when I've simplified it to significant figures, 2, 3 sig figs. It's a lot of fun saying sig figs, and you'll learn to say it a lot in chemistry. So that's the final answer of that question. The working out up here, guys, there's no requirements for significant figures, but this final answer was specified as 3 significant figures, so make sure you write that down, otherwise you're going to lose a mark. On to the last part of this question. So the last part of this question isn't necessarily stoichiometry, but again shows that questions rely on other parts of the content. So even if you feel like you're a genius at stoichiometry, make sure you understand the other principles as well, because often they'll still apply to stoichiometry-based questions. So, getting into the question. The equation for step 3 of this process is reproduced below. I'm just going to trust that it is. It is an exothermic reaction, gives us the delta H value. It is carried out at 900 degrees Celsius in atmospheric pressure. Use your understanding of reaction rates and the Shuttle-Giza principle to explain why these conditions are employed for this reaction. Well, there's a couple of reasons why this would all occur. It's carried out at 900 degrees Celsius. So, why would that occur? Well, what happens when we increase temperature? It's one of the key ways we can actually increase the reaction rate. So, high T increases reaction rate. That's certainly one element we should be focusing on. However, low T increases yield. And how did I know that? Well, it's an exothermic reaction. So that means a lower temperature is actually going to increase the yield or the forward, or favor the forward reaction, whatever way you want to look at it. So there, I'm going to write down, therefore, compromise of 900 degrees C. Now I know that might not seem like a low temperature, but considering this reaction could be held at thousands of degrees Celsius, the temperature was most likely actually lowered down to 900 degrees in order to ensure there was some sort of decent yield. Now, the other thing we're looking at is atmospheric pressure. Now, the only thing that changes with pressure, really, is actually is dependent upon the molar ratio on the left-hand and right-hand side for the number of moles of gas. On the left, we see in total we have 9 moles of gas, and on the right, we see we have 10 moles of gas overall. So that means low pressure favors the forward reaction and increases the yield. Admittedly, this isn't by much as the molar ratio is very close to one another, but it will still favor it. Now, additionally, the reactions will still proceed reasonably well at atmospheric pressure. Reaction proceeds well. And the reason why I'm saying that is because the difference in moles of gas on the left and right is not significant enough to justify lowering the pressure significantly. So basically all I'm saying with that little bit there, guys, is that there's not much point in lowering the pressure further because there isn't a significant difference in the moles of gas between the reactants and the products. So essentially, guys, the high temperature used is a compromise between the rate and the yield. And ultimately, although a high pressure favors, increases reaction rate, there's a compromise. Oh, sorry about that, guys. There is a compromise. There we go. Increases rate. There is a compromise of atmospheric pressure. Awesome. And notice that I've identified 5 elements here, and that's where the 5 marks are coming from. You could have written more things down, but these were the key elements you were looking for. Fantastic, guys. Hope that went well for you. One of the key things I think that you really need to look into this question was the fact that there was so much information given in that first initial block. I still remember one of my questions from my Year 12 exam, and I actually panicked because of the amount of information that was given to me and spent way too long tackling the question. What I've learned is to actually skip over that initial text, read the actual question itself, read part A, read part B, whatever it might be, and work out what you need. Fantastic. I look forward to seeing you in the next episode.